the handouts from chapter 2 of a different book, and I will cover this in my lecture. Is the lecture being recorded now? Let me check.
Yes, sir.
Okay, thank you. Okay, sorry about that. Let me grab the definition of Laplace transform. Some of the slides, the chapter you will study on your own. For example, the complex algebra. So I'm not going into the details, but I want to show you what you need to know about the complex algebra. So Z is the vector in the complex plane, which has real axis and imaginary axis. And you can write down the in the vector form as well as in the scalar form. The magnitude and the direction can be written like this, and the polar form can be written this way. This is just a review. And if you want to find out the complex conjugate of two polar numbers, they are the two complex conjugates. Each complex uh, vector has its conjugate by replacing this positive sign to negative sign. That's it. So when you are doing this, you just have to replace this negative sign. And Euler's theorem says that cosine theta can be written in the series like Taylor's expansion theorem. So this is just a formula which you might need for Laplace transform. So I'm going to write down directly jumping to the Laplace transform. Before I jump to the Laplace transform, I want to mention some more. If you manipulate these Euler theorem, e to the j, and do the addition, you get cosine theta, and do the subtraction, you get sine theta with the two subtraction of the two Euler's formula divided by 2j. So let's go ahead and do the Laplace transform formula. How are you going to write down Laplace transform can be written in this form? So if I take one example, for example, if I ask you, can you find out the Laplace transform of a e to the negative at for t are positive or equal to 0? So you will apply this formula 0 to infinity a e to the negative at e to the negative st dt. So if I combine these two exponents, I can write down a plus s times t dt. A is outside the integral sign from 0 to infinity. So what's the formula for, what's the integral of this? So you remember e to the negative at. If you do the integral, it should be e to the negative at divided by the derivative of this exponent, which is with respect, which is negative a. Similarly, if you want to do the e to the negative a plus s, the integral of this one, so you will do the e to the a plus s t divided by the derivative of this exponent with respect to t, which is a plus s negative sign outside. I'm sorry, this is alpha, not a. Is it alpha? Let me double check. It's alpha. It doesn't matter, both are symbolic, but anyways, so right now, can I write down like this? A is outside the parentheses. This is a. What is this? If you plug in negative a s plus a, if you plug in infinity, can I write down like this? Correct? What is 1 over infinity? 0. So this goes to 0, this goes to 1. So negative 1 times negative gives you positive, correct? A over s plus a. So Laplace transform of a e to the negative at is equal to a over s plus a according to this form. Let's do one more basic example. Laplace transform of a unit step function. Like if you give a step value of a in time domain, how are you gonna show me in the Laplace domain? Laplace domain is like a complex plane, okay? It has real root, which is usually denoted by sigma, imaginary root, j omega d. So you will see later down the road that the Laplace plane defines the step response. For example, if the roots are located on the real axis, they don't have any they don't have any oscillation factor, uh, or zeta is equal to 1 or greater than 1. But if they're in the complex plane, the time response looks like a is oscillatory functions. And here, if there are the roots are located on the imaginary line, there is no damping at all. So we will study it. I believe I mentioned in lecture. I think I like in previous lecture. This is a little blurry. That tell me, yeah, maybe. So let's go over here. So let's do one more problem to understand the basic method how to find out the Laplace. So f of t is a. So a is outside, e to the negative st divided by negative s. So a over negative s 1 over infinity minus e to the so it's the same thing. So you get 1 here, you get 0 here. So 0 minus 1 gives you negative. So a over s is the Laplace transform of a. So let's do one more example. Laplace transform of a sine omega t. So the way I'm going to solve this, I'm going to apply this into this formula. I know that I just wrote down this formula earlier. Yeah, a, it is easy to write down in terms of exponent e to the j theta. So let's write it down here. E to the j theta minus e to the negative j theta over 2j. And a is outside the parentheses. So this would be the formula. So look, can I write down theta as omega t? Because I have written down this theta as omega t. So I'm going to write down the equation of the Laplace transform as 0 to infinity. 2j is outside because this is a constant. E to the j omega t minus e to the negative j omega t. I'm sorry, I forgot to write down e to the negative. Now what I'm going to do here, I'm going to show you that if I multiply this inside, so can I write down like this, j omega minus s, or if I write down like this, s minus j omega. So if I take the integral a over 2j outside, that will help me to find out the answer for this one. So can I write down like this integral limits of infinity and 0? So what will happen to this term? They will go. This will go to. So you are left with 1 over s minus j omega minus 1 over s plus j omega with a over 2j outside the parentheses. Because t is a negative infinity and 0 will cancel out. 1 becomes 0, other becomes 1. So don't worry about that much. So like this one, you can simplify this as s minus j omega, s plus j omega, and you are left with s plus j omega minus s plus j omega here. A over 2j is outside. So you'll have s is cancelled by s. So 2j omega. So 2j omega over j is, this is what? What is this? This is s square, like a square minus b square formula, a plus b into a minus b. So minus b square, which is minus j omega whole square, which is equal to what? S square plus omega square. So j is cancelled by this j. So did I, this 2 is also cancelled. It's also there. So you will see this one is can be written down as a omega over s square plus omega square. So this is the Laplace transform of a sine omega t using the basic definition method of the Laplace transform. So when you go home, you can find out the Laplace transform of a cosine omega t using the same method, but this time you will use this formula. And at the end of the day, you will see that this becomes equal to as over s square plus omega square. So this is a table which you should take a look when you go home. I'm just copying pasting some of the formulae. So the Laplace transform of a time domain function are written here, and these are the time domain functions here written here. The one which we just saw is sine omega t and e to the negative at. There are some properties which you can write down, that if the function is translated, suppose if the function is this is a function, and if it is translated to another time delay, for example alpha, so I this is f of t right at the 0 time, but this is starting at t minus alpha, a little bit delay. This function is translated to alpha time, then you can represent this t minus alpha. This section tells me that it is delayed by alpha minutes or alpha time. So how are you gonna represent in the Laplace transform? So the Laplace transform will consider this alpha delay as negative alpha s times f of s. For example, if I ask you, okay, that the sine omega t, if I ask you that sine omega t is delayed to 2 units, okay, and you have to find out the Laplace transform, then first of all you will look the Laplace transform of sine omega t. What is that? Because f of s is the omega, so I can write it omega over s square plus omega square. But now I have to take this into consideration. How are you gonna use this? So I'm gonna use this as multiplication of exponent 2 times s. You see my point? So that's the complete correct formula answer for the Laplace transform, which has a delay function in the time domain, which you can multiply with the exponent function in the Laplace domain. Some of the more properties or the Laplace transform given in the table format, which you may need solving the differential equations using the Laplace transform. This one you may need it. This one you may need it. So what is this? This is actually the time derivative. For example, if you have x dot, this is how you will write. If you have x double dot, second derivative, then you have s square x in the s domain minus s, x of 0 minus x dot. So please write down these two formulae because I'm gonna assign you a homework problem with which is related to finding the Laplace transform, finding the solution using the of differential equation using the Laplace transform. So this you may need over there. So we will solve such problem today. This is the one which is delayed function. So I just mentioned here. So you make sure you understand, you read this graph correctly. So if it is starting from 0, then you will not have any subtraction in the time. But if it is having subtraction of some time, it is starting at a little bit delay of that time. And that delay is considered in negative alpha s multiplied by the Laplace transform of f of t. So if you have a pulse, how are you going to show me the pulse formula? So this is a pulse function. And what is the Laplace transform of a pulse function? So can I write down this formula? This function can I write down like this function, the step function, and then it is delayed at t naught. This is t axis. This is starting. So what if you add these two functions, which are two step functions? One is at a over t naught. One is at negative a over t naught. Then you can easily find out the Laplace transform. So what is the Laplace transform of a step function? You know that we just solved a over t naught is a step value 1 over s. Agreed? And what is this delay? Is this the same step function? I would write this down. A over t naught. This is starting a negative a over t, starting at delay of this function. You see my point? So how are we gonna write down the Laplace transform? So e to the negative t naught s 1 over a over. So if you add these two functions together, this is for first function, the second function, then you get a pulse function. Okay, pulse function of the width a t naught. So let's add these two functions together. A over t naught 1 over s minus e to the t naught s a over t naught 1 over s. So can I write this down like this? A over t naught s is factored out. So 1 minus e to the negative t naught s. So this is the Laplace transform of a pulse function of width t naught. So this is the same thing which has been described in our book in a different way. So this is a function Laplace transform. Do you understand that? Now, in order to find out the Laplace transform of a impulse function, take the pulse function, which is this width, and limit the width to 0. So can you take this? Let's apply limit t0 t naught goes to 0 a over t naught s 1 minus e to the negative s t naught. So let's apply the limits. So if I plug in a 1 minus e to the 0 over 0, so this becomes 1 minus, so it is 0 over 0. In that situation, you have to apply a L'Hopital rule. the way this works that you have to take the derivative of the numerator and derivative of the denominator with respect to t naught. So I'm gonna show you how gonna derivative of the numerator divided by the time derivative of the denominator with respect to t naught, and then apply limit. So what is the derivative of the numerator? Is 0. So negative negative become positive. So e to the negative s t naught over s times a. I forgot to write down a here outside. So now you plug in t naught as 0. Limit. Now you plug in t naught as 0 over here. What become it becomes 1 over, I would say a is outside, so a over s naught, as. Sorry, I forgot to write down this s here. So this is also multiplied by s. S is cancelled by, so you are left with a. So the impulse function is represented, impulse of magnitude a is the same magnitude. It is in our book, the representation of impulse is by this um, delta function. So the Laplace transform of delta is 1 of magnitude. So let me show you this table. You see unit impulse is 1 delta t function. Another case is this is done. So another case is if you have alpha t. Uh, Let me show you. Sorry, if you have alpha t of any function, so fs plus alpha. For example, Laplace transform of sine omega t. What is the function of what is the Laplace transform of this function? Omega over, but it says you have to write down rather than s square, you have to write down that delay. So can I write down, actually I would write this down as s plus alpha whole square plus omega square. So this is coming from this property. If the in time domain it is multiplied by letter e to the negative alpha t, you have to add this delay. Similarly, if you have, let me show you this formula here. There is another thing which you have to remember is initial value theorem. and final value theorem. That is very helpful to see the end behavior and initial behavior of any dynamic system. So what I mean by that, initial value theorem, that f of t function can be written as sf of s limit. Okay, let me ask you, in the if the time is 0, what is the frequency? 1 over time, 1 over 0, which is infinity. So this is 0. So limit s goes to infinity. So it's the same thing. Left hand side is in time domain where time is taken at 0 time. And if it is at taken at 0 time, you have to take the inverse of 0, which is infinity. In the right hand side, because s is frequency. Okay, s is the Laplace transform, which is also. So this is a formula which is known as the initial value theorem. So what it means by that, so let me show you over here. Initial value theorem. And the other theorem is the final value theorem. It is opposite to initial value. So what it means by the, look, I can write down this as the final value theorem, and it will help me what is the final value. So if t is infinity, because we know that 1 over s or 1 over frequency, if it is infinity, so 1 over infinity is what? 0. So that's why frequency domain s is limiting to 0 when time is limiting to infinity. So remember, this is the final value theorem, this is the initial value theorem, and they are helpful to find out the end behavior of the graph. Now comes talk about the inverse Laplace transform. Do you know partial fraction expansions? So let's do one problem. Can you write this? You need to know about the partial fraction expansions. So can I write down this in terms of first quarter, because this is factor 1, factor 2. I can write down in terms of first partial fraction expansion coefficient, second coefficient. Do you understand what I'm doing here? So I wrote down the left hand side, which is f of s, in terms of two separate partial fraction expansion coefficients, a1 and now my job is to find out a1 and a2, and then I will do the inverse Laplace, and I will show you how to do the inverse Laplace in a bit. So look, can I multiply both sides? This is the left hand side, this is the right hand side. Can I multiply both sides by the denominator of the left hand side? So look, can I write over here? Multiply both sides by s plus 1 and s plus 2. And now compare the coefficient of s1. I would say s power 1. What is the coefficient on the left hand? 1, a1 plus a2, equation 1. Compare the coefficient of s0, which is constant. Left hand side is 0, sorry, 3. It is 2a1 plus a2. So you have two equations, two unknowns. Can you find out? Can you find out a1 and a2? So if you do the math, so let's do it together. So if you multiply this by 2a1 plus 2a2 equals to 2. and just subtract this, subtract this, subtract this. So 1 equals to, this cancels out. So you're left with negative a2. So that means a2 equals to negative 1. And now you can plug it in either one. Let's plug it in equation number 1. So I can write down 1 equals to a1 minus a1. So that means a1 equals to 2. So now once you get these two expansion coefficients, then you can plug it in the right hand side and take the inverse Laplace transform. So let's do this math here. So the right hand side, I'm gonna plug in a1 as 2 divided by s plus 1 minus 1 divided by s plus 2. Now what you have to do after you find the expansion coefficients, you have to take the Laplace, inverse Laplace transform. We write in like L power negative 1. So can you take the L power negative 1 2 over s plus 1? How would you find this out? So I'm going to show you this table. This table will help me to find out the inverse Laplace. You have to go from the column uh, Laplace transform to the, so let me show you over here. Can you compare which row is best suited for? If I take a look, row number 6 is best suited for our case. 1 over s plus is, go back from here. This is negative power inverse Laplace from Laplace. So how would I write? I can write this down 2 e to the negative t. Agreed. Similarly, Laplace transform of the other term 1 over s plus 2, and do the same thing. Use row number 6 similarity and go write this down at e to the negative a. In place of a, it is written 2t. Agreed. So I'm writing down the complete answer of our Laplace inverse of f of s equals to 2 e to the negative t minus, yeah, minus sign. This is a minus sign. This is a negative sign here. So minus e to the negative 2t. Do you understand this question? Now, in this question, you see the numerator has a higher degree of polynomial. In that case, you have to do the long division method. When the numerator polynomial is higher degree than the denominator polynomial, then you have to do the long division. So what is this? S square plus 3s plus 2. So I can write this down. S square plus 3s plus 2. Because you cannot apply the partial fraction expansion coefficients on the degree of polynomial numerator is greater. It should be smaller. So can I write down like s cube plus 3s square plus 2s? So I can write this down, the answer, the quotient plus remainder. So I can write this down as, I can write this is my quotient. So s plus 2 plus s plus 3 divided by s square plus, I would write this down in terms of two factors, which are s plus 1 and s plus 2, because I have to write down in terms of partial fraction. So now this can, the what is the inverse Laplace of this one? Inverse Laplace of s is the time derivative of the delta function. Inverse Laplace of 2 is the delta function. this you already know from the table. And for this one, we just solved this question. I believe we just solved this question, right? Yes. S plus 3. Oh, so I can write this down again. And this is my answer for the right in the that term which is over here. So I can write this down here. This is the Laplace inverse. So I can write down the whole equation. The inverse Laplace of this function. This is S. Sorry, this is my f of S equals to time derivative of the delta function plus 2 times delta t plus 2 times e to the negative t minus e to the negative 2t. This is a complete answer for the Laplace inverse Laplace transform. Now let us solve this question. We know that the numerator degree is less one less, so we can apply the. So if you see the s square, you can write this down as in terms of a s plus b. Do you know what I'm doing for partial fraction? You may have done this before. So 1 degree less than the denominator degree in the partial fraction expression. So if it is square, the numerator should have as plus b. Agreed? So multiply both sides on the denominator. So I can write this down. So multiply both sides by the denominator of the left hand side. So I can write this on as plus b. So there is one thing I'm missing here. So what is the root of this one? You cannot do like this. I have to do some operation here. So look, what are the roots of this thing? So you will tell me, Professor, the roots are -1 plus minus 2j, right? You remember the quadratic formula from your high school? So what is b here? -2 plus minus 4 minus 4 times 20, 522 times a. So it is -2 plus minus 16j. So I can write here 4j. Agreed, divided by 2. So this is how you get the roots of a polynomial which has a complex roots. Okay, in that case, how can I write down? Can I bring this on the left hand side? Can I write down like s plus 1? Can I write down like this s plus 1 plus 2j? So now what you have to write down, you have to replace this by these two factors. So and in the numerator, I'm gonna show you what you're gonna do. So 2s plus 12 can be written by like this. So I can write down 2s plus 12 over s square plus 2s plus 5. I can rewrite this one in terms of two factors, s plus 1 plus 2j, s plus 1 minus 2j. Now I'm gonna do multiply whole side both side by the denominator of the left hand side, so I can write down 2s plus 12 a. Uh, I want to show you something here. This one, if you go to the contents list, I have made a video for the. This is question number 3. Right. This is the complex root method, and the problem which we are trying to understand from this example, which is on page 35 of your book. And I have modified this example. First part, I would explain the complex root. The second part, I would explain how to solve the differential equations uh, from here. So I would start from here. So let me tell you, when you see the complex roots or when you see quadratic roots in the denominator, the first thing which you have to do is to find out whether it can be discretized or not. So if we can find out that it has a discrete root, how can you find it out? By just applying the quadratic formula, the high school knowledge. What is the quadratic formula? Do you remember for finding out x equal to minus b? I'm skipping it because we already know that. And what is equal to what you get in this problem? That you first of all, the denominator, if it is quadratic, find out through this root method whether can it be discretized. If it can be discretized, then you can go to the simple matter other than s. You can write it. You have to apply two partial coefficients, partial fraction coefficients for the square degree, like quadratic degree. If it is 2, s power 2, you have to apply bs plus c, s squared plus 2s plus 5. I think you guys already have done such problems in the past, so I think you are understanding. And then you have to multiply the both sides. Okay, first of all, let me find out the discrete root. How will I find out a? You see, this is a discrete root. Okay, so multiply both sides by s.
and evaluated s equals to 0. All right. So 3 over, I'm not writing down that term again because this is just a repetition. Evaluate s equals to 0, you will get a. And if you multiply by s over here, it will evaluate. Once you evaluate, this whole term will be, the second term will be vanished. Okay, because this is s you multiply. So I'm left with a only, and that a is equal to, that means a is equal to 3 over 5. This is our first coefficient. In order to find out coefficient B and C, we have to do a certain method. You have to multiply both sides by the denominator of the left hand side. Try to understand. Multiply both sides. So let me write this down. B plus C, do this one. So, and now we have to compare the second coefficient, S to the power 1. Do you see S on the left hand? No. For term C, no, because you are multiplying both terms by S outside. So this is not a constant at all. So A is equal to what? You got the same answer from the discrete root method. So you are verifying your answer. What answer did we get? We got the same answer from the discrete root method. And now we have to compare the second coefficient, S to the power 1. Do you see S on the left hand side? No, you do not. So this is 0. On the right hand side, you see 2a plus plus c. That means c is equal to minus 2a. That means c is equal to what? Minus 6 over 5. Do you understand what's happening here? So this is what the correct answer. Now we have to again compare the second option A, which is, this is how you will find out S. Understanding what's happening here? I just plug in the value inverse Laplace is g of 1 over s, 3 over 5. This is row number 2. For the unit step, you get 1 over s. So we have not a unit step, but the magnitude is 3 over 5 for the unit step. So the answer is, for this term, it is this one. Now, in order to solve this one, what I want to mention here, let's take this out. S plus 2. And then here comes the quadratic formula which we did. And now try to understand, this is an important step. What I'm trying to show you here, these are the two roots, complex roots which we already found from the first step. All right. So these are very helpful. Why they are helpful? So the roots for this denominator are these two roots. So if I write them down, I can write them down like this: s plus 1 square plus 2 square. Do you understand this thing? I just split up these two roots, multiply them, and you get this answer. If you are still not clear, let me go back to your old knowledge. A plus b, a minus b. What is that equals to? A square minus b square. So if I write this term as s plus 1 plus 2 iota multiplied by s plus 1 minus 2 iota. So this term is a, this term is b, this is a, this is b. So if I write down s plus 1 whole square minus b is what? Minus 2, 2 iota square. This is b. So what do you get? S plus 1 whole square plus 2 square. This is what I wrote down here. I broke it up for your help to understand it from the scratch. A plus b minus into a minus b. So this is very helpful. Now you can apply the method. You can apply the Laplace transform. If I go back to the Laplace transform table. So you would need these two rows in order to solve this answer. Now you have to look. This is which row is matching our term This term, this one, 21. That's correct. But in 21, if you see this is A, this is also A, but this is not A. Like we do have different numbers. We should have same number in order to match exactly. But how can we write down? How can we get the same number? Can we split up? Can we split up 2 into 1 and 1? Can we do that? The way we just multiply, we have to split this 2 into 1 and 1. So let me write this down here and let me copy and paste here this term. And over here, I'm going to make the form so that we should be able to apply the inverse Laplace. So still we are not matching exactly because in the denominator, this is 1. In the numerator, this is 2. How can we make it 1? Just split it up. Do you understand me? Now it is exactly in the same shape. S plus a square. This is a is 1 in this case. S plus a square, which is 1. So we can apply this method on the Laplace inverse. So the Laplace inverse for this term is e to the power minus t cosine omega is what? If you look at here, this is the mega, which is 2. 2 times 2. Now, if I go up a little bit, so exactly this is exactly matching with our term here. So if you take, so exactly I would not say I have to multiply by 2 and divide by 2 because omega is being multiplied in the numerator and I don't have 2. In order to bring 2 into the numerator, I have to multiply and divide by 2 so that the term should not be um, D-shaped. So 2 will go here. So I would say 2 will go inside and s plus 1 whole squared plus 2 squared. So now you can apply the Laplace inverse to this method, which is 1 by 2 outside e to the power minus t and sine 2t. Now we have solved this question. Only the thing is minus 305 should be taken care of. So minus 305, I should write here.
I'm going to share with you this video. And the thing is, you have to solve these questions at home. I'm going to share with you these problems from problem number from 2.1. Yes, at least, yeah, 2.12 to 2.6. Okay, these are the problems which I'm going to assign you from 2.13 to 2.25.